Okay, let's unpack this. Imagine a 4th of July weekend, usually a time for celebration, maybe some fireworks, clear skies. But instead, it suddenly morphs into this unimaginable nightmare of rising water across central Texas. For so many people, the devastation seemed to just erupt out of nowhere, a terrifying flash flood that swallowed roads, homes, even entire communities. But as we've meticulously sifted through the sources you've shared with us, a much more intricate and frankly kind of astonishing picture emerges. This wasn't just some random act of nature. It was a really complex dance of powerful atmospheric forces, a uniquely vulnerable landscape, critical systemic failures, and, the undeniable shifting backdrop of our climate.
Yeah, what's really fascinating here, and what this deep dive is really going to try and reveal, is how multiple sort of seemingly disparate elements aligned with almost, cruel precision to create such a profound and tragic impact. We're not simply looking at, a bad weather day. Not at all. Instead, we're going to pull back the layers on a complex interaction of the atmosphere, the very earth beneath our feet, and the human systems that are designed or supposed to be designed to protect us. Our mission today is really to cut through the noise, provide you with a clear, structured understanding of this very complex event, hopefully offer some aha moments and surprising connections that will leave you truly well-informed, far beyond just the initial headlines.
So let's begin where any storm truly starts, with the sky itself. The meteorological causes behind this event are particularly compelling, especially what our sources refer to as the stalled moisture machine. When I first read that phrase, it sort of conjured images of something almost mechanical, relentless, like something out of science fiction. But the sources make it clear. The mid-level remnant of Tropical Storm Barry, combined with a pretty common weather feature known as a trough, didn't just pass through Texas. It became effectively stuck, or stalled, directly over central Texas, like a massive leaky hose pipe just turned on full blast and left sitting in one spot.
That's a very vivid and actually quite accurate way to describe it. This is no fleeting summer shower, that's for sure. A mid-level remnant of a tropical storm, even one that's weakened considerably over land, still carries an immense amount of moisture. And crucially, it carries latent heat from its origins over the warm ocean waters. Latent heat, for those maybe unfamiliar, is the energy that gets absorbed or released during a phase change. So in this case, water evaporating from the ocean surface, then later condensing into clouds and rain. It's like stored energy, fuel for the storm. Now, when this moisture-laden system encountered a trough, which is basically an elongated area of relatively low atmospheric pressure, the conditions became perfectly ripe for something truly extraordinary. Troughs are known for encouraging upward motion in the atmosphere, which, leads to cloud formation and precipitation. But the key, as you highlighted, was that stalled aspect. This wasn't a system that was moving along briskly. Instead, it created what meteorologists call a mesoscale convective complex, or an MCC. You can sort of picture a cluster of individual thunderstorms, but they're not just randomly popping up. They're organized into one giant, long-lived, and incredibly efficient rain-producing factory. And the reason it parked itself, as our sources explain it, is because the atmospheric steering currents, those are the high-altitude winds that typically push weather systems along. They became incredibly weak, or maybe even contradictory, right over the hill country. It was like a meteorological traffic jam. The system literally had nowhere to go.
I'm really intrigued by this idea of a storm parking itself. It sounds almost impossibly unlucky just sitting there. But practically, what does that actually mean for the sheer volume and the continuous nature of the rain it can unleash? Is it literally just like continuously drawing moisture and dumping it? Or is there a more complex cycle happening within this MCC?
It's a bit of both, actually, yeah. Think of it less like a single static cloud just sitting still and more like a continuous regenerative rain machine that's fixed in place. When an MCC parks itself, it isn't just one storm cell that's stationary. It's actually a dynamic system where new storm cells are constantly forming on its leading edge. They draw in fresh, warm, moist air, often pulling it up from the Gulf of Mexico, in this case, while the older cells dissipate on the trailing edge. Meteorologists call this process training, because the individual cells move over the same area one after another, like boxcars on a train track passing over the same spot. Right, and this constant regeneration, this continuous influx of moisture means the system keeps tapping into a deep well of atmospheric water vapor. So instead of a storm sweeping through, delivering maybe a few hours of intense rain and then dissipating or moving on, this mesoscale convective complex just sat there and cycled. It relentlessly dumped an extraordinary and continuous volume of water over the Texas Hill Country for a really extended period, sometimes for 12, 18, maybe even 24 hours or more, right over the exact same coordinates. This mechanism directly leads to that prolonged, exceptionally intense rainfall concentrated over a very specific confined area, which of course maximizes its destructive impact. It's kind of the difference between turning on a garden hose and pointing it at one spot for 5 minutes versus leaving that same hose running full blast for 2 days straight over the same small patch of ground. The ground just has no chance to absorb it.
And when you talk about extraordinary rainfall intensity, the numbers our sources provide are truly shocking. Almost beyond belief, really. We're talking about local totals of up to 20 inches of rain in some spots over just 2 or 3 days. That's just a staggering amount of water. Few places anywhere in the world can handle that kind of deluge. But it wasn't just the total accumulation that was so devastating, was it? It was the sheer speed and concentration of it. Our sources really emphasize peak intensity reaching approximately 5-10 inches per hour. 10 inches in an hour that's not rain, that's a literal deluge.
You're absolutely right. The rate of rainfall is what really distinguishes a dangerous flash flood from just, a heavy rain event. It's all about how fast it comes down. To really try and grasp 5 to 10 inches per hour, I mean, consider that in many parts of the country, an entire month's worth of rain might be 3 or 4 inches total. Here, we're talking about that amount, or even double or triple that, falling in a single hour. It's like standing under a waterfall, honestly, not just a heavy rain shower. And large areas, according to the sources we looked at, saw 6.5 inches in just 3 hours, which even that is an incredibly rapid deluge that would overwhelm most drainage systems, most landscapes. But the truly immediate and dramatic effect, the moment where the scale of this event truly becomes apparent, I think, was its impact on the Guadalupe River. Our sources describe it as simply unbelievable, rising an astonishing 22 feet in just 2 hours, and then almost inconceivably topping 29 feet in under an hour at one particular point.
29 feet in under an hour. That sounds less like a river rising and more like a literal wall of water. It's almost unimaginable to even picture that. I mean, what are the physical implications of water moving with that kind of speed and force? What does that actually do to the landscape and, well, everything in its path? I'm really struggling to visualize that kind of power.
You're absolutely right to struggle with that image, because it truly is difficult to comprehend. It's not a gradual rise, not the way most people picture a river swelling during heavy rain. No, that kind of rapid accumulation and movement of water creates an incredibly powerful and destructive phenomenon. It's often referred to as a wall of water, or sometimes a hydrodynamic bore. Just imagine the immense volume of water, now supercharged by gravity because it's on steep terrain, and it's confined often to a narrow channel. It accelerates downwards. It doesn't just flow, it scours. It doesn't just inundate, it pulverizes. The force generated is easily enough to sweep away vehicles, cars, trucks, as if they were just toys. It can destroy sturdy bridges, concrete bridges, and obliterate structures directly in its path. We're talking about mature trees being snapped like twigs, entire houses lifted clean off their foundations, large sections of riverbanks just vanishing, eroded away in minutes. There's often a particular sound associated with it, too, that survivors describe. A low, distant rumble that quickly escalates into this terrifying, all-encompassing roar, usually accompanied by the crashing sound of debris trees, parts of buildings being carried along. And crucially, there is virtually no time for the ground to absorb any of this water, none. Nor is there time for the river's normal channels and banks to accommodate it. It instantly overwhelms them, spilling out into floodplains and any low-lying areas with devastating speed and force. This incredibly rapid onset is precisely why these types of flash floods are so deadly. They leave almost no time for people to react, to evacuate, or even to truly understand the danger until it's literally upon them. It transforms from maybe a swollen but manageable river to a devastating, destructive torrent in mere minutes.
Wow, so it's becoming crystal clear that it's not just the amount of rain, but how the very land itself seems to conspire with the water, turning what might be heavy rainfall elsewhere into a catastrophic flood here. This brings us perfectly to the land's crucial role and the environmental vulnerabilities that make Central Texas, specifically the Hill Country, such a notorious place for these sudden, violent floods. Our sources consistently refer to it as Flash Flood Alley. But what exactly is it about this landscape that makes it so uniquely prone to these sudden, almost immediate surges of water?
That's a perfect way to phrase it. The land doesn't just passively receive the water. It actively contributes to the intensity and the destructive speed of the flood.
Yeah.
Central Texas, especially the Hill Country, is defined by very specific geological features. It's primarily characterized by a limestone bedrock, which often creates what geologists call karst topography. This basically means the soil cover is often quite rocky, it's thin, and it's highly compacted. Think of it like trying to pour water onto a granite countertop versus pouring it onto a thick sponge. The compacted soil in the Hill Country is much, much closer to that granite countertop. It has very low permeability. It simply cannot absorb intense rainfall quickly or in large volumes. As a result, the water has really nowhere to go but to flow rapidly over the surface as runoff. And furthermore, the terrain itself is characterized by steep slopes, narrow canyons, and deeply incised river valleys. This topography acts like a giant natural funnel. So when immense volumes of water from that stalled storm hit this non-absorbent, steep landscape, gravity just takes over immediately. The water is channeled at high velocity directly into the river systems and the low-lying areas. It accelerates its flow, dramatically increasing its volume in a very, very short amount of time.
Okay, so instead of soaking in like it might in other places, it just rushes over everything, picking up speed as it goes. What does that mean for the natural buffer zones that rivers usually have? You know, the areas alongside that might typically absorb some of this excess water in a slower flood.
Precisely. It creates what's called sheet flow water, moving as a broad, fast-moving sheet over the surface rather than infiltrating the ground. Now, most healthy river systems elsewhere have natural floodplains. These are typically broad, flat areas adjacent to the river channel. During high flows, these areas can temporarily store excess water, essentially acting as a natural sponge and a buffer zone, slowing the water down. But in the hill country, because of the steep, narrow canyons and that non-absorbent ground, these natural buffer zones are severely limited, or in many places, they're virtually non-existent. The water gets funneled directly and forcefully into the riverbeds and their tributaries. This accelerates its flow and dramatically increases its volume within a really compressed time frame. It's almost like a landscape engineered by nature itself to rapidly convert heavy rainfall into raging torrents. This inherent geological structure, often combined with relatively sparse vegetation in some areas that might otherwise slow down runoff a bit, is precisely why the region has earned that grim moniker Flash Flood Alley. And it's why even a heavy, but maybe not necessarily record-breaking, amount of rain rate over a short period can turn into an absolute catastrophe here. The land just can't handle it.
It's surprising, isn't it? Almost tragic, really, to see a place repeatedly hit by these kinds of events. Because our sources reinforce that this isn't some new phenomenon for the Guadalupe River corridor. This historic flash flood pattern tells us this area has seen major flash floods before. They specifically cite the devastating floods of 1978, 1987, 1998, and more recently, 2015. But it raises a really profound question for me. If these patterns are so well known, if this is famously Flash Flood Alley, why were people still so vulnerable? Why did it seem to catch so many off guard, even after decades of these repeated devastating events?
That's an absolutely crucial observation, and it really cuts to the heart of the complex challenges of living in, well, a naturally hazardous region. Those past events you listed, 1978, 1987, 1998 to 2015, they were all, as our sources explain, intensified by the exact same terrain and geology we just discussed. They weren't flukes. They serve as critical historical data points, demonstrating a clear, recurring pattern of extreme vulnerability in that specific area. Understanding these historical flood patterns is absolutely fundamental for any kind of future risk assessment, for mitigation planning, for public education. It really should inform everything from building codes and land use planning to emergency preparedness drills and public awareness campaigns. The fact that despite this deep known history, people were still so vulnerable points to a multifaceted problem, I think. It's not just about knowing the risk in some abstract sense. It's about the effectiveness of mitigation strategies. Are the dams adequate? Are the building codes enforced? It's about the reach and the reliability of the warning systems, which we'll get into. And yes, perhaps there's a degree of complacency that can inevitably set in over time between major events. Populations change, too. People move into these beautiful scenic riverfront areas who may not be fully aware of the historical flood patterns or the true speed of these events. Development sometimes expands, maybe into existing floodplains, putting more structures and more lives at risk. There's also this challenge of what researchers call flood memory, basically, the tendency for communities to forget the severity of past events as years pass without a major incident. Especially for newer residents who weren't there for the last big one, it highlights a persistent and, I think, dangerous disconnect between historical knowledge, which is often held by long-term residents or, local experts and emergency managers, and the actual on-the-ground readiness and resilience across the entire community. This isn't unique to Texas, of course. It's a challenge faced by many, many communities living in high-risk zones all over the world.
And when water rises at that unimaginable speed we were just talking about, 29 feet in under an hour, minutes, literally minutes, make all the difference between life and death. Which brings us squarely to the human response, or perhaps the critical gaps in our ability to warn people effectively. Our sources highlight some deeply concerning failures in alerting the public, particularly with what they describe as delayed and insufficient warning systems. The first flash flood emergency declaration was issued at 4:03 a.m., and this is a direct quote from the sources, just minutes before the waters surged. To me, that sounds like almost no warning at all when you're facing that kind of surge. And this idea of poor reception and maybe even contradictory advice being given to people who are in imminent danger, that's just deeply concerning. Can you elaborate on the specific issues found in places like Kerr County?
The timing of those warnings is absolutely critical, yes. And in this case, it really represents a profound failure of what should be a robust public safety system. For a flash flood event of this magnitude and speed again, where a river can rise by dozens of feet in under an hour, a warning issued just minutes before the water surges is, unfortunately, almost useless from a practical standpoint. Effective flood warnings, especially for flash floods where things happen so fast, require significant lead time. Ideally, you want hours if possible to allow for orderly evacuation, for people to maybe secure some property, and just generally prepare for that immediate, devastating impact. When you have a literal wall of water moving at that speed, every single minute counts. And a warning issued at 4:03 a.m. for a surge that happened almost immediately after, well, it's a devastating indictment of the system's ability to protect lives in that moment. It's like shouting a warning as the boulder is already halfway down the hill towards you. It's too late. Now, in Kerr County specifically, the sources detail a really critical, almost unbelievable absence of siren-based alerts along the river corridor. Instead, there seemed to be a near-exclusive reliance on cell networks. Things like wireless emergency alerts, WEA, sent to smartphones. Now, while text message alerts are a powerful tool and they have their place, they are inherently vulnerable during major emergencies, especially in certain terrains. Reports from residents there indicated widespread issues, including poor reception, which, let's be honest, is a common and predictable problem in rural, hilly terrains like the hill country, where cell tower density is lower and the terrain itself can block signals. But beyond just poor reception, people reported getting alerts late, messages not coming through at all, or perhaps most dangerously, even receiving contradictory advice from different sources or at different times. Imagine being woken up in the middle of the night, maybe by a frantic phone call from a neighbor, or perhaps a faint alert sound from your phone, only to find your cell service is spotty. Maybe the message itself is delayed by minutes or hours, or worse, you get conflicting information. Evacuate now. Shelter in place. Which way do you go? This creates immense confusion and panic right at the moment where clarity and immediate decisive action are paramount. It fundamentally undermines the effectiveness of any warning system. Sirens, while maybe perceived by some as an older technology, offer a distinct and vital advantage in these situations. They broadcast an undeniable, immediate auditory alert to everyone within earshot, regardless of whether they have cell service, regardless of their phone's battery life, or even whether they're awake and looking at their phone. Their absence in a known flash flood alley region and the apparent over-reliance on a less resilient, less universally accessible system like cell alerts seems to have had dire life-threatening consequences here. It meant that even for those few who might have gotten some kind of warning, the time to actually act on it was virtually non-existent.
That paints such a grim picture. It really does beg the question. Were the folks on the ground, the emergency managers, the forecasters, were they doing the best they could, but with less? Were they fighting an uphill battle? Because our sources also point towards systemic weaknesses outlined within the very organizations designed to protect us. Specifically, the National Weather Service, or NWS, and its parent agency, NOAA, the National Oceanic and Atmospheric Administration. It's mentioned that multiple meteorologist roles at the key NWS Austin-San Antonio office remained unfilled leading up to this, and that crucial leadership had retired early due specifically to NOAA budget and staff cuts, which the source attributes to the Trump administration. What does it truly mean when the very agencies designed to protect us are facing these kinds of resource constraints? And what do the experts cited in our sources suggest was the potential impact of these cuts on this specific flood event?
Well, this is a deeply concerning aspect of the whole crisis, isn't it? Because it highlights potential vulnerabilities within the very institutional backbone of our nation's warning and response systems. When sources indicate that multiple meteorologist roles at a critical regional forecast office like NWS Austin San Antonio remained unfilled, and that senior leadership retired early sighting budget and staff cuts, well, it paints a pretty clear picture of an agency operating under significant strain, effectively being asked to do more, maybe much more, with less. See, meteorologists, especially those at local NWS offices like the one covering the Texas Hill Country, play this vital, multifaceted role that extends far beyond just issuing the initial forecasts you might see on TV. They are the frontline interpreters of incredibly complex atmospheric models. They're constantly refining those models with real-time data that's streaming in from radar, from ground sensors, satellite imagery, local storm spotter reports. They possess, or should possess, An intimate, granular knowledge of the local topography, exactly how specific watersheds react to rainfall, the unique flash flood vulnerabilities of an area like the Hill Country, even down to where localized high watermarks are typically found in certain communities. This kind of local expertise is absolutely crucial for issuing highly localized, precise, and critically timely warnings, especially when conditions are changing as rapidly as they were in this event. And beyond just the forecasting, these NWS meteorologists are also critical for coordinating directly with local emergency responders, fire departments, police, search and rescue teams, county emergency management offices. They provide the most up-to-date, granular information that these local agencies absolutely need to make life-saving decisions on the ground. Where should they deploy resources? Which roads need to be closed now? Which specific neighborhoods need to be evacuated first? This isn't just a one-off phone call. It's supposed to be an ongoing, dynamic dialogue that refines and updates as the situation evolves, sometimes minute by minute. So, experts suggest, and again, it's important to frame it that way, as we're reporting on what these sources indicate, that these staffing cuts could have significantly delayed forecasting efforts. They could have hampered the continuous refinement of the flood models as the event unfolded. And they could have fundamentally impacted that critical coordination with local emergency responders. When staffing is stretched thin, there are simply fewer eyes on the incoming data streams. There's less capacity for the rigorous, continuous model refinement necessary as complex weather patterns evolve. And there's reduced bandwidth for maintaining those vital communication channels with local authorities who are making decisions in the field. This isn't just about a reduction in headcount on paper. It can genuinely impact the agency's ability to fully utilize advanced forecasting software, to integrate new data streams effectively, and to ensure that the most accurate and timely information flows seamlessly to those who need it most to protect the public. An understaffed agency, even one populated by highly dedicated and skilled personnel, can face significant challenges in scaling up and responding effectively during a rapidly unfolding, high-impact event like the Texas floods. It potentially creates critical gaps in the warning chain that perhaps could have been avoided with full resources. It definitely raises a critical question about the level of resources we allocate to our nation's foundational emergency preparedness infrastructure, particularly in an era where we know extreme weather is increasing.
That's a really powerful point. It highlights how decisions made maybe miles away or years before concerning budgets and staffing can have direct, tangible, and potentially tragic impacts on people's lives during a specific weather event. So, okay, what does this all mean when we step back and try to look at the even bigger picture? Beyond the meteorological causes, beyond the landscape vulnerabilities, beyond the systemic warning failures we've just discussed, is there a larger, more pervasive factor at play here shaping these events? Our sources pivot to what they call the broader view by linking these kinds of extreme weather events, specifically these slow-moving, high-moisture storms, to the broader context of climate change. Specifically, they name prominent experts like UCLA's Daniel Swain and Andrew Dessler from the Texas Center for Extreme Weather. What exactly are their arguments, and how do they propose global warming is impacting events like this Texas deluge?
Yeah, this is where we try to connect the dots from an individual devastating event like this one to the overarching long-term trends that are shaping our planet's climate system. Scientists like Daniel Swain and Andrew Dessler are definitely leading voices in the climate science community, and they argue pretty strongly that these kinds of slow-moving, high-moisture storms are indeed linked to a changing climate. Their core argument really hinges on a fundamental and very well-established scientific principle. A warmer atmosphere holds more moisture. This isn't speculation, it's basic physics. It's often referred to as the Clausius-Clapeyron relation. For every degree Celsius, that's about 1.8 degrees Fahrenheit, that the atmosphere warms, it can hold approximately 7% more water vapor. So think about it. When you have a storm system, particularly one like this, that's drawing vast amounts of moisture from a warm body of water like the Gulf of Mexico, it now has access to a significantly larger reservoir of potential rainfall, just because the air itself is warmer. This increased moisture capacity in the atmosphere translates directly and powerfully into the potential for heavier, more intense precipitation events. We saw that in full, horrifying force with the Texas floods. Those peak rainfall rates of 5, even 10 inches per hour are pretty much textbook examples of what can happen when an atmosphere that is supersaturated with moisture decides to dump it all at once. Furthermore, while it's maybe a more complex area of ongoing research, a warming climate can also influence atmospheric circulation patterns, the large-scale winds. This could contribute to more occurrences of stalled or slow-moving storm systems, precisely like the mesoscale convective complex we detailed earlier that parked over Texas. Changes in large-scale weather patterns, like shifts in the jet stream's path or the persistence of blocking high-pressure systems, can cause weather fronts and storms to become stuck over certain regions for extended periods, rather than moving along their typical trajectories. Imagine a river, and suddenly a large dam appears, holding back the flow. That's kind of what these blocking patterns can do to weather systems in the atmosphere. So when you combine an atmosphere that's capable of holding significantly more moisture with these potentially altered circulation patterns that allow storms to linger and continuously dump that extra moisture over one specific spot, well, you create conditions where extreme precipitation events like the July 2025 Texas floods become more likely, as the experts put it, and potentially more intense when they do occur. This perspective really highlights that what we're witnessing isn't just a series of isolated, unfortunate weather incidents. Instead, it strongly suggests a dangerous long-term trend that's being exacerbated by a changing climate. It implies that communities in vulnerable areas like Central Texas's flash flood alley will likely face an increasing frequency and intensity of such events in the future. And that adds yet another critical and urgent layer to the profound challenge of preparedness and resilience. It pushes us to consider not just how we react to individual disasters, but how we adapt to a fundamentally shifting climate reality.
Wow. As we pull all of this together, it becomes just profoundly clear that the July 2025 Texas floods were not just a single cause, right? Not just a simple weather anomaly. It was a true confluence, a perfect, devastating storm, you could say, of meteorological conditions, geographical vulnerabilities, critical systemic challenges, and emergency response. And all of this playing out against the undeniable backdrop of a rapidly changing climate. This wasn't just bad luck. It was a devastating intersection of multiple compounding factors all hitting at once.
Absolutely. When we dissect this event, we can really clearly identify 5 major interconnected contributing factors that converge to create this catastrophe. First, the meteorology. You had the mid-level remnant of Tropical Storm Barry, combining with a persistent trough, which stalled directly over central Texas. This fed continuous record-breaking heavy rain over the region for days, sometimes at those unimaginable rates of up to 10 inches per hour. Second, the geology and environment. The unique flash flood alley landscape of central Texas, its karst topography, the rocky compacted soil, the steep funnel-like terrain. It meant there was virtually no absorption. Water just rushed over the surface at incredible speeds, leading to exceptionally fast and destructive runoff, dramatically funneling water into river systems like the Guadalupe, causing it to swell by dozens of feet in mere minutes. Third, those systemic warning gaps. The public warnings were dangerously late issued, literally minutes before the water surged, and they proved insufficient. There was that critical absence of siren-based alerts in key areas like Kerr County, forcing reliance on unreliable cell networks. Residents reported poor reception, late alerts, and in some heartbreaking cases, even contradictory advice, leaving people confused and with almost no time to react safely. Fourth, institutional weakness. The National Weather Service, specifically the NWS Austin-San Antonio office, was operating with reduced staff and resources due to prior budget and staff cuts. Experts suggest this potentially hindered their ability to provide the most accurate, timely, and localized flood forecasting possible, and critically, it may have impacted their vital coordination with local emergency responders who are making decisions on the ground. And finally, number 5, the climate influence. The scientific consensus linking warmer atmospheres to an increased capacity for moisture. This fuels heavier, more intense, and potentially slower-moving storms, making future events like this terrible flood not just a possibility, but a growing likelihood in the years and decades to come.
This deep dive really shows us, doesn't it, that to truly understand an event like the Texas floods, we have to look far beyond just the immediate headlines about rainfall totals. It's about peeling back layers, and each layer, as you just laid out so clearly, reveals a critical lesson, a different facet of vulnerability that, when they all combine, created a true cataclysm. The aha moment here isn't just that it was a big storm, but that this disaster was really a complex tapestry woven from natural forces, human decisions, systemic vulnerabilities, and long-term environmental shifts.
And that raises a really important question for all of us, doesn't it? It's about how incredibly interconnected these systems are. The weather, the land, our warning systems, our institutions, the climate. Vulnerabilities in one area can drastically amplify problems across the board. The meteorology was undeniably extreme, yes, but the unique geology of the land made it exponentially worse. That geological vulnerability is historically well known, it's documented, yet the human-designed warning systems failed in critical ways at the critical moment. And all of this is playing out on a global stage that is fundamentally being reshaped by a changing climate, making these extreme interactions more probable in the future. Knowledge, like we've explored today, is most valuable when it's understood and actually applied. And here the knowledge points to urgent areas for critical thought, for reevaluation of our systems, and for concrete steps towards future preparedness. We can't just fix one piece of this puzzle, like just improving cell alerts, and expect the whole picture to change. It really demands a truly holistic approach to understanding and addressing risk.
As we've seen today, the July 2025 Texas floods were a harrowing, truly tragic reminder of how powerful natural forces can converge with human systems, sometimes with just catastrophic results. In an era where extreme weather events are becoming not just isolated incidents, but increasingly likely and intense, this deep dive leaves us with a profound question for you, our listener, to ponder. What does true preparedness look like for communities built in challenging, historically flood-prone landscapes like Flash Flood Alley? Especially when they are facing not only these historical patterns, but also the accelerating, sometimes unpredictable forces of a changing climate. How do we adapt? How do we learn from events like this? How do we build genuine resilience in the face of such overwhelming power? Thank you for joining us for this deep dive. We really hope this exploration has given you a clearer, more nuanced, and deeply informed understanding of the complex forces at play in the Texas